Okay, welcome back. Right now we're going to be continuing on with this unit 15.1. Basically, we're just following the trends of the textbook. So if you've got the textbook, of course, you can follow along with these videos much easier. In this video, we're going to be covering enthalpy changes, changes in solution, changes, sorry, changes in solution. So what these enthalpy changes in solution are, it's kind of what we've covered already. Like I said, I made one small mistake in that last video with the enthalpy change of hydration. If you see the last video, I think it was video 1 of this series, I covered all the different enthalpy changes that we needed to do. And I made a mistake with the enthalpy change of hydration. I kind of mix it up with enthalpy change of solution or of solvation. So I'll fix that in this video at least. So we've got two different enthalpy changes we're going to cover in this video. Delta H of SOL, which I like to imagine of solvation, but you can imagine it's of solution in your textbook, of solution, and delta H of hydration. And we're going to define what these are right now. So delta H of solution, if we were to write down the equation, or an example of it, a general example of it, it's that we have Mg, we'd have some sort of ionic compound in its solid phase, and we dissolve it into solution, where it breaks up into its ions, and now it is solvated. So this is the enthalpy of solvation. That's why I like it, because now it's solvated, and this can be positive or negative. So it can be endothermic, where the temperature of the solution will decrease when we dissolve it, or it can be exothermic, where the temperature increases. Temperature can increase. So this delta H of solution of solvation can be positive or negative. And what it is, if we were to define it, it's the energy gained or released by an ionic salt when dissolved in solution. So basically, we just take the salt, we dissolve it in the solution, and your textbook, I believe it says, infinitely dilute solution. Because of course, right, we dissolve this into the solution, and these ions are going to interact in solution, so they're going to attract a little bit in solution. But as we dissolve more and more and more and more, we're going to have more and more M plus and more, oh, this is X minus in solution, and the M pluses are going to repel each other, and the X minuses are going to repel each other. So since they're repelling each other, that's why we need infinitely dilute solution, because we're taking away the effect that as we put more and more salt into the solution, we're going to get more and more intermolecular forces occurring between the ions in the solution. And then we got the delta H of hydration. Delta H of hydration. So I messed up, like I said in that first video, of solvation with hydration. In delta H of hydration, we can do this as an example. So once we've got these ions in gas phase, M plus or X minus in gas phase, we can dissolve these gases into a solution. So first they're in gas phase, and then we put them into the aqueous phase, and they're positively charged now, and this is X minus aqueous phase. So basically we're dissolving a charged gas species into the aqueous phase, and this is an exothermic process. So why it's an exothermic process, you can imagine, right? We're going from a very disordered high energy phase, and we're turning it into a liquid phase. So when we turn it into a liquid phase, it's going to be releasing heat. It's going to be losing some energy to the environment. So this is exothermic. So delta H of hydration is typically exothermic. So let's look over, right? Let's look at your book. I'm just going to grab mine right now. Basically, let's go over the worked example in this video. I don't want to end this video too early. So we got a worked example. So what the graph gives us, let's look at what the Born-Haber cycle gives us. So of course it's giving us a Born-Haber cycle, and we need to find the unknown value. So what it gives us is our overall equation is going to be sodium hydroxide solid into sodium hydroxide. Okay, we're just basically dissolving it. So let's look at what we're doing. The question gives us this sodium hydroxide. It gives us our delta H of lattice enthalpy. So remember, lattice enthalpy is breaking up an ionic solvent, ionic solid, into its ions in the gas phase, OH minus. This is gas phase and gas phase. And then we've got a few more. So basically, it gives us this arrow down here. So delta H of lattice is 900 kilojoules per mole. And then now we've got sodium hydroxide. The energy drops delta H of hydration. It gives us, as we need to hydrate both molecules, we need to hydrate H plus and we need to hydrate OH minus. And it gives us those as negative 424 and negative 519. And we know hydration is to dissolve it into solution. So sodium positive aqueous plus OH minus as aqueous. And it wants us to figure out the unknown down here. So it wants us to figure out what this is right here. And this is delta H of solvation. So right, delta H of solvation would just be if we took sodium hydroxide and we dissolved it into its ions in solution, OH minus aqueous. So basically that's our delta H of solvation. So it wants us to solve the unknown. And we do this the exact same way as we would before, right? We're trying to solve this delta H of solvation. Like we said up here, it's always an exothermic process. So we know that this needs to be a negative value. So delta H of solvation. And we do just like we would before. We want to arrive at this value. So we have 900. Then we want to come back down to this value. So plus negative 424 plus negative 519. And our delta H of solvation is equal to, let me get my calculator out. There we go, 900 minus 424 minus 519. We get a negative 43 value. So delta H of solvation is negative 43 kilojoules per mole. And remember that this needs to be negative because we're going basically, or no, delta H of solvation doesn't need to be negative. This one needs to be negative. Delta H of hydration is always negative. So we can't say that this is definitely going to be negative in this case. So what this tells us, actually, working through this way, what this tells us is that when we dissolve sodium hydroxide, the temperature of the solution is going to increase. We're going to increase the temperature of the solution. So we can see this in class maybe, when we get back to school. We'll see that the delta H of solvation for sodium hydroxide, the solution gets very, very hot after a time. And that's because because it's releasing energy into solution. So okay, join me back for the next video. And like I said, if these questions still aren't making that much sense to you, we are going to solve all the questions at the end of the chapter. So hopefully through solving the questions, you'll see what's expected. Thank you.